In the previous two videos, we've done a couple of things. We've established some ideas about logarithms, and the first one was the definition. And the definition that we gave for logarithms was basically that y is equal to the log base b of x meant the very same thing as x is equal to b to the y. And this was something that you should have learned in an algebra class. And basically it takes the mystery out of logs. This statement is kind of mysterious to students, but if we rewrite it this way, a lot of times that makes it a little more understandable. And then we had properties. Of logarithms. We had verified them in terms of the natural log, but the verifications could be adjusted for logs of any base. I'm going to use the base c instead of b because we're going to be using b for a different purpose in these statements. And so remember the statement that the log base c, we had said natural log, of a times b is the log base c of a plus the log base c of b. So we had that property, and basically the property says that logs change multiplication to addition, harder operations to easier. We had a second property, the log base c of a raised to the power r was r times the log base c of a. And notice here that logs change an exponent to a multiplier, a harder operation to an easier. Then as a result of these two properties, we were able to verify that the log base c of a over b was the log base c of a minus the log base c of b. Your book will list lots of other properties, but these are ones that are important to us. The next thing that we saw, all right, was where there was an important limit. We did not prove this limit, all right, and we don't have the tools to prove it at this point, but it was the limit as v approaches 0 of the quantity 1 plus v to the 1 over v was equal to e. And we just looked at basically at numbers on an Excel spreadsheet and saw that that's what happened as v got close to 0 from either the left or the right hand side. And finally, we had a derivative formula. And basically this said that the derivative with respect to x of the natural log of x was 1 over x. Now there's something that I need to say here, is that notice that the definition, of course, applies to logs of any base, all right, any legitimate base. The properties of logs, again, apply to logs of any base, any legitimate base. But this definition only applies to the natural, or this derivative only applies to the natural log. Okay, so what we want to do is we want to see, well, what happens in the case of other logs with other bases. And so to start with, let's think about this statement. Y is equal to the log base b of x. Well, if y is equal to the log base b of x, according to the definition, x is equal to b to the y. So if y is equal to log base b of x, then x is equal to b to the y. If x is equal to b to the y, then their natural log should be the same. So the natural log of x should be the same as the natural log of b to the y. And now notice we have the natural log of something being raised to a power, so that power can be brought out as a multiplier. So then we have the log base b of x is equal to y times the natural log of b. Hence, natural log of x is equal to y times the natural log of b. Dividing both sides by the natural log of b, we'll have y is equal to the natural log of x divided by the natural log of b. But remember, y was the log base b of x. So the log base b of x is equal to the natural log of x over the natural log of b. I'm going to write that as 1 over the natural log of b times the natural log of x, and you'll see why in a few minutes. All right, so this is an important formula we have. This is a special case of what you might have called the change of base formula in an algebra class. Now, how is this helpful? Well, on your calculator, you can compute natural logs and you can compute common logs. Natural logs are logs base e, common logs are logs base 10. But you can't compute log base 7. All right, but here, this formula gives us a way of doing that. If we needed to know the log base 7 of 5, well, according to this formula, x is being played by 5, so this would be the natural log of x. B is being played by 7, so this would be the natural log of 7 on the bottom. It would be the natural log of 5 divided by the natural log of 7. And I have an Excel spreadsheet. Notice that if we look at this formula, it's the natural log of 5 divided by the natural log of 7. And 0.82709 is the result. So this would be approximately 0.82709. That would be the rough value, and that we could get a decimal approximation of this expression, and you could do this computation on your calculator. All right, now let's take a look. How do we use this to take derivatives? Well, all right, if we look at this, let's suppose y is equal to the log base 2 of x. Well, then dy dx is the derivative with respect to x of the log base 2 of x. And according to our formula, that would be the derivative with respect to x of 1 over the natural log of 2 times the natural log of x. All right, this 1 over the natural log of 2 is just a number, okay? It's constant, a constant factor. All right, and so I can take it out. Sort of like when I'm taking the derivative of 3x squared, I can think about the 3 outside of the derivative, just take the derivative of x squared, and multiply by the 3 when I get all done. So I can think of this as 1 over the natural log of 2 times the derivative with respect to x of the natural log of x. And I know how to take the derivative with respect to x of the natural log of x. That is 1 over x. So this becomes 1 over the natural log of 2 times 1 over x. Or this would be 1 over x times the natural log of 2. So the derivative with respect to x of the log base 2 of x is 1 over x times the natural log of 2. Let's take a look at a more general case. All right, the derivative with respect to x of log base b of x. So if we take this derivative with respect to x of log base b of x, using the formulas we've established up above, this would be the derivative with respect to x of 1 over the natural log of b times natural log of x. Again, assuming b is constant, this is a constant factor. All right, so we could take this 1 over the natural log of b outside of the formula, outside of the derivative, and we'd have 1 over the natural log of b times the derivative with respect to x of the natural log of x, and that's 1 over x. So we'd have 1 over the natural log of b times 1 over x, which is 1 over x times the natural log of b. And this would be the derivative formula for the log base b of x. 1 over x times the natural log of b. All right? Notice a couple of special cases. All right, first, the derivative with respect to x of the natural log of x. We know what that is. But let's take a look at this. This is going to be the derivative with respect to x of the log. Remember, the base of the natural log is e, log base e of x. And that, by this formula, is 1 over x times the natural log of e. We've seen that the natural log of e is 1, so this is just 1 over x. So we see that this is that one special case that we've seen before of this formula. Okay, and that's what makes the natural log so special. Okay, now let's take a look at this. This is a place where students can make a mistake because they may forget about this base here since it's not written. So remember that if I take the derivative of the common log of x, that's the derivative with respect to x of the log base 10 of x. And that's going to be the derivative of log base 10 of x is going to be 1 over x times the natural log of 10. So remember, this is how we take the derivative of the common log. All right, now in the next video, we'll go on to use some of these formulas for excuse me, to take more involved derivatives.